Greetings. Welcome to today's session. So let me start off with a brief recap of what we did yesterday. So in the previous class, we were looking at the notion of transfer function. What was the system transfer function? We saw that the class of systems under study, which is the class of linear time invariant causal dynamic systems, like could be represented in general as a linear ordinary differential equation with constant coefficients, as shown here. And if we take the Laplace transform of this equation and apply zero initial conditions and take the ratio of the Laplace of the output variable to the input variable, we get a quantity called as the transfer function. Okay, so this is how we derive the transfer function. And in general, a transfer function is a ratio of two polynomials in the complex variable S. So there is a numerator polynomial n of s, which is of order m, and there is a denominator polynomial d of s, which is of order m. Okay, so and for causal systems, anyway, n is greater than or equal to m. So we will be dealing with proper transfer functions, and when n is strictly greater than m, we call it as a strictly proper transfer function. Okay, so these are some terms that we should know. Then we defined what are called zeros and poles of the transfer function. Zeros are nothing but the roots of the numerator polynomial of the transfer function. Poles are nothing but the roots of the denominator polynomial of the transfer function. Okay, so and we stopped with a definition of stability. So essentially, we saw that a dynamic system that they are studying is said to be bounded input, bounded output stable, provided its output always remains bounded in magnitude for all time whenever we give any bounded input to the system. Okay, so that is what is called as BIBO stability or bounded input, bounded output stability. And I left you with this exercise to do, wherein I gave you two systems, and then I asked you to essentially obtain the transfer functions and determine the unit step response and comment. Right. So in today's class, let's start with these two examples, and then we will do these exercises and interpret the results. Okay, from there. So let me start with the first problem, where the first system is governed by this equation, right? Y double dot t plus 3y dot t plus 2y of t is equal to u of t. Okay, so let us say we take Laplace transform on both sides. Okay, so let's say we apply the Laplace transform on both sides. So if I apply the Laplace transform, what's going to happen? So for y double dot t, we are going to get a squared y of s minus s times y of 0 minus y dot of 0. So that is what we have. Then if I take the Laplace of y dot, I am going to get s times y of s minus y of 0. So we have the factor 3 anyway associated with y dot. And then we essentially take the Laplace of y of t, which is only y of s, and on the right hand side we have u of s. Okay, so then what do? We apply all the initial conditions to be 0. So we take all the initial conditions as 0. So we apply 0 initial conditions. So what's going to happen is the following, right? If I apply 0 initial conditions, y of 0 becomes equal to 0, y dot of 0 becomes equal to 0. Okay, so these terms vanish, right? So once these terms vanish, what happens? So if I collect the terms involving y of s, we are going to get s squared plus 3s plus 2 multiplied by y of s. I'm just collecting the terms involving y of s, and this is going to be equal to u of s. So if we cross multiply, we get the plant transfer function or the system transfer function, right? Which is nothing but the ratio of the Laplace of the output to the Laplace of the input variable under 0 initial conditions, right? So that is going to be 1 divided by s squared plus 3s plus 2. Okay, so this is what we get as the plant transfer function. So I hope this is clear to everyone, right? So this is quite straightforward, and this essentially gives us, how to get this. Essentially shows us the process of obtaining the system transfer function. Okay, so that's what we have. So we can immediately make some observations. We can immediately observe that the value of n is 2. Okay, it's a second order system, right? So we can write from here itself that the value of n is 2 and the value of n is 0, right? So because why? The what is n? N indicates the small n indicates the order of the highest derivative of the output variable, which in this case is 2, right? We have the second derivative as the highest derivative. And m is the order of the highest derivative of the input variable, which in this case is 0. So n is equal to 2. And the denominator polynomial d of s is a second order polynomial, as we can readily observe. That is going to be s squared plus 3s plus 2. And the value of m is 0. And the numerator polynomial is just 1, right? So it's just a constant. Okay. And we can immediately observe that there are no zeros for this transfer function, because the numerator polynomial is just a constant. And if we look at poles, how do I calculate the poles? I need to solve the denominator polynomial to be equal to 0. So I need to solve s squared plus 3s plus 2 equals 0. This can be factorized as s plus 1 times s plus 2 is equal to 0. So this implies that the poles are at -1 and -2. Okay, so these are the two poles of this transformation. Okay, in fact, we can represent this in a graphical manner. Okay, so let me represent poles and zeros in what is called as the S plane. So let me draw the complex plane. Okay, so this is the real axis, this is the imaginary axis, and okay, so this is what is called as the S plane. Okay, so nothing but the complex plane. It's just called the S plane by convention because we are drawing values of the complex variable S. Okay, so now in this plane, we can immediately observe that there are two axes, right? The real axis and the imaginary axis. Some people will call the real component as sigma and the imaginary component as j omega. Okay, so they will call it as the sigma axis and the j omega axis. Okay, so these are all terms that we should be aware of. And we can observe that this is a two-dimensional plane and two-dimensional space, right? And the imaginary axis divides this plane into so-called two half planes. Okay, so what are these two half planes? So if we look at this two-dimensional plane, the space to the left of the imaginary axis is what is called as a left half plane. Okay, so everything to the left of the imaginary axis is what is called as the left half plane. Okay, abbreviated as LHP. And whatever is towards the right of the imaginary axis is what is called as a right half plane. Okay, abbreviated as RHP. Okay, so I hope it's clear what is meant by the left half plane and the right half plane. So any complex variable S is in the left half plane means its real part is negative, right? So that's another interpretation we can have. And if any complex variable S is in the right half plane, essentially, we are going to have the real part of the what is it, complex variable to be positive. Okay, so that is the consequence. Okay, so now what we also do is that, like, when we essentially indicate it, right? So indicate this poles and zeros, right, in the right of plane and the left of plane. So what we do is that, like, we use some symbols. Okay, so what are these symbols? Poles are typically indicated by using a cross mark. Okay, so that's how poles are indicated. Okay, so this is just a graphical representation. Okay, so sorry. Okay, so and then like zeros are indicated by an O. Okay, so that's how poles and zeros are indicated. So once again, let me repeat. Poles are indicated by using a cross mark. Zeros of the transfer function are indicated by putting a O, okay, or a circle. All right. So that's how they are graphically indicated. So in this particular example, the two poles are at -1 and -2. Okay, so I have just marked them on the complex plane or the S plane, and we can see that the two poles are at what to say? These are the two poles, right? So they are at -1 and -2. So that is why I marked them on the negative real axis. Okay, so at -1 and -2. Okay, so these are the two poles, and we can observe that both poles in this particular case lie in the left of plane. Okay, so please remember this. We will come back to this point later. Okay, so both the poles of this system transfer function lie in the left of complex. Okay, so now having derived the transfer function, calculated the zeros and poles, and plotted them in the complex plane or the S plane. So let us now calculate the unit step response. Yeah, any questions till now in this example? All right. Okay. So let's go ahead with the unit step response. Unit step response means, as we already know, u of t is 1. So u of s is 1 by s. So this implies that y of s is going to be equal to p of s times u of s. Okay. So that is going to be equal to 1 divided by s times s squared plus 3s plus 2, which can be rewritten as 1 divided by s times s plus 1 times s plus 2. Okay. So when we are talking about the unit step response, we want to get y of t, right? Is it not? So how do we go from y of s to y of t? We need to take the inverse Laplace transform, right? So if I want to take the inverse Laplace transform, I need to do partial fraction expansion, right? So essentially, we take this factor. So we can see that there are three factors, s plus 1 and s plus 2. So what we do is that like we can
Hello. Hello.
Hello. I think
I can't hear the professor.
the sir got disconnected.
Hello, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
I think there's some power outage at IIT Madras, so consequently, I have to wait for it to come back. Otherwise, I can't record the meeting. So my request is that, like, please stay in this room, okay? I will also stay muted. Let's hope that the power comes back in the next 5 minutes, okay? Yeah, then we will continue. All right?
Okay, sir.
Yeah, sorry
Yes,
about
sir.
it. Please stay in the same meet room, okay? Yeah.
Okay.
Hello, am I audible?
Yes, sir.
Yes, sir.
Okay, sorry. I think power has still not come back, but then like I think I could fortunately make some alternate arrangements, like so that we could essentially continue with our class. So sorry about the unexpected delay, but let's continue. Right. So I hope the screen is visible and my video is audible.
Yes,
So
sir.
let's continue from where we left off. So thank you for waiting. So essentially, what we have here is this response, like function that we want to calculate. So we have the expression for y of s. Like now we need to essentially take the inverse Laplace transform of it. Like so, what we do is the following: we do partial fraction expansion. Like given that there are three factors, so we'll have three factors in the partial fraction expansion. So I have to write it as a by s plus b by s plus 1 plus c divided by s plus 2, right? So this is how we do it. And I'm sure all of you would be familiar as to how to take partial fraction expansion, but however, I will do it once more. So if I have to calculate the factor a, what I do is that like I multiply both sides by s, because s is the factor which is appearing in the denominator of the term involving the residue a. So once I multiply both sides by the factor s, what will I get? Left hand side will become 1 divided by s plus 1 times s plus 2. S will cancel off. So a by s will become just a. And then the remaining two terms will become bs divided by s plus 1 and then like plus cs divided by s plus 1. Okay, so this is what will happen to the terms. Now what we do, we essentially substitute the root of that term that we multiply with, right? So we multiply it by the factor s, so the root of s is going to be s equals 0, right? So if you substitute s equals 0, what I will get is on the left hand side I will get 1 by 2 and right hand side I will get a. All right. So because the terms involving b and c will go to 0, right? Because we have s in the numerator. When we substitute s equals 0, they vanish. Now, if I want to calculate b, what do? I essentially multiply by s plus 1. Okay. And consequently, what will happen to the left-hand side? I will get 1 divided by s times s plus 2. That is going to be a s plus 1 divided by s plus b, okay? And then like c times s plus 1 divided by s plus 2. So consequently, what we will have is that like if I essentially substitute the root of s plus 1, which will be minus 1. So the left-hand side will become minus 1. The right-hand side will be just b. Okay, so b will be equal to minus 1, right? So then if I look at the factor c, I need to multiply both sides by s plus 2. So then consequently, the left-hand side will become 1 divided by s times s plus 1. And then the right-hand side will become a times s plus 2 by s plus b times s plus 2 divided by s plus 1 plus c. Okay, so that's what will happen to the right-hand side, right? Now, what do? We essentially substitute s equal to minus 2, okay, because the root of s plus 2 is equal to s equals minus 2. So once we do that, the left hand side becomes 1 by 2, the right hand side becomes c. Okay, so these are the three residues. So consequently, what will happen is that like we have now obtained the partial fraction expansion of y of s. So this will be 1 by 2s minus 1 divided by s plus 1 plus 1 divided by 2 times s plus 2. Okay, so this is what we will have. So now can you help me with the inverse Laplace transform? What will be the inverse Laplace transform 1 by 2s?
1 by 2.
It will just be 1 by 2, right? And what about
E raised to minus.
it will be e power minus t. right? Yeah. And what about the,
E power minus
yeah,
2t.
I think I seem to be getting some echo, yeah. So I request everyone to mute whenever they are not answering, please, so, yeah. So the last term will be 1 by 2 e power minus 2. Okay, so this is what we will have, right? As the response function, right? Y of t. So this is the unit step response of this particular system. Okay, so essentially we can immediately observe from here that as t tends to infinity. Okay, so what do I mean by t tending to infinity? As time keeps on increasing, right? What do you think happens to the value of y of t? If you substitute t equals infinity, what do you get?
1 by 2.
So y of t tends to 1 by 2. That's right, right? So because why? Because we can see that as t tends to infinity, the other two terms, like e power minus t and e power minus 2t will go to 0, right? Because they are exponential terms with a negative exponent. Okay, so now two observations are extremely critical. Okay, so we can see that the output or the response function, right, has exponential functions of time. Okay, so that is observation number one. So for the class of systems that we are considering, always the output function, like when we analyze with respect to any input, will always contain exponential functions. But that is unsurprising because in mathematics, it's a well-known result that when we are essentially dealing with the class of linear ordinary differential equations with constant coefficients, we are always going to have exponential functions as the unique solution, okay, for that system of equations, okay. So if we take a linear ODE with constant coefficient, it has been shown that only the exponential solution is the unique solution, okay, for that class of equations. So that's what is reflected here. Okay, so second observation is the following. The poles appear as the exponents. Okay, in the output function or exponents of the exponential terms. Let me put it. Okay, so what do I mean by that? Because what are the two exponential terms, functions, e power minus t and e power minus 2t, right? The exponents are -1 and -2. And as we already have observed, -1 and -2 are the poles, right? We already calculated, right? So -1 and -2 are the poles of this particular transfer function, right? So we can immediately observe that, interestingly, the response function or output function has exponential terms, and the exponents of the exponential terms are the poles. Okay, so what do we mean by exponent? So if we have an exponential function e power at, okay, the real what to say, the parameter a is what is called as the exponent, okay, of the exponential function. Okay, so I hope that is clear, right? So when we have in general an exponential term like e power at, the parameter a is what is called as the exponent of the exponential. Okay, so that's something we should remember. Okay, so please keep in mind these observations. All right. So now, having looked at the first problem, let's go to the second problem. Okay, so one. So what was the second problem? If you recall,
Sir,
the second,
excuse me,
yeah.
sir. First point you
Yes,
mentioned,
please.
like solution will be like something you mentioned. I didn't get that, sir. Output response function as exponential.
So yes. So you can see that in y of t we have the exponential functions, right? E power minus t, e power minus 2t, and so on, right? So a function of the form e power at is an exponential function, right? This is an exponential, right?
Yes, sir.
Okay, yeah. So I just told a general mathematical result as an aside. So what I meant was that, like, when you have linear ordinary differential equations with constant coefficients, mathematicians have proven already that the only solution to that equation is the exponential function. Okay, so I just wanted to connect the physics and the mathematics. Like, that's all I wanted to do by that statement. Okay, but the bottom line is that, like, we can readily observe by doing this example that the only term which appear, the only time varying function, right? Function of time is, so I hope all of us can agree with that, right?
Yes, sir.
So any other questions?
Uh, I think your voice is breaking,
Okay.
sir. Actually, last. I don't know whether it is for me
Okay.
or for
Sorry.
everyone.
Yeah, for me also it's
Uh,
breaking.
I,
No, no, no problem, sir.
okay. So I think I'm sorry. Yeah, but yeah, I'm sorry. See, what happened was that the power supply went away at IIT Madras, and internet is also disrupted. So I am joining using another internet, what to say, this connection, right? So whose signal may be further, right? So please bear with me in today's case.
Yes, sir.
Yes, sir.
So now let us go to the second example. The second example is the following. So we consider the system y double dot t plus y dot t minus 2yt is equal to u of t. Okay, so this is the second example, right? Yeah. So we essentially do a similar analysis here, right? So first, let us take a Laplace transform on both sides. So let's do this exercise. So let's say we take the Laplace transform on both sides. Okay. So what happens? Like, we will get s squared y of s minus s of y0 minus y dot 0. That is the Laplace transform of the second derivative. Okay. And then we have the first derivative, right? So the Laplace transform, the first derivative is going to be s times y of s minus y0. And then, like, we have the y term. So we are going to get minus 2y of s. And that's going to be equal to u of s. Okay, so that's what we have. Then we apply zero initial conditions. So if we apply zero initial conditions, what do we get? Let's analyze. Okay, so once we analyze apply zero initial conditions, y of 0 will become 0, y dot of 0 will become 0, and this y of 0 also will become 0, right? So once we have that, like, we can immediately see that this equation can be simplified to s square plus s minus 2, the whole thing multiplied in y of s, that's going to be equal to u of s, right? So if we cross multiply, we are going to get the Planck transfer function p of s, which is the Laplace of the output variable to the Laplace of the input variable under zero initial condition as the following, right? So we are going to get it as 1 by s squared plus s minus 2. Okay, so this is going to be the Planck for the system transfer function for this example. Okay, so I hope it is clear. So now we do similar analysis, right? So I'm sure by now I think we know what to do, right? So first, let's identify the values of n and m, right? So what are the values of n and m? So n is going to be 2, m is going to be 0, and the denominator polynomial of the transfer function is going to be s squared plus s minus 2. Sorry, this is the denominator polynomial, right? So denominator polynomial is d of s. The numerator polynomial n of s is 1. So consequently, what will happen? There are no zeros, okay, for this particular transfer function. As far as the poles are concerned, how do we find the poles? We solve the denominator polynomial is equal to 0. So we need to solve s squared plus s minus 2 equal to 0. So this can be obtained as s minus 1 times s plus 2 is equal to 0. So this will give me s equal to 1 and s equals minus 2 as the two poles. Okay, so these are the two poles of the transfer function, right, in this particular case. So now let us see what happens. Okay, so let's plot the S-plane. All right, and then like we will calculate the unit step response, and then like we will see what observations we made. Okay, so this is the real axis. This is the imaginary axis. This is the S-plane. Okay, so always you should label what we are drawing. Okay, so this is the origin. Now, if I use the cross marks to denote the poles and zeros, so we have one pole at -2, one pole at 1. Please remember, this is the LHP, right? The half plane to the left of the imaginary axis is the LHP. The half plane to the right of the imaginary axis is what is called as a right half plane. Okay, so we can immediately observe that one pole lies in the right half plane. Okay, so this is a very important difference, right, compared to the previous example. In the previous example, the poles were at -1 and -2. So both poles were in the left half complex plane. In this particular example, one pole is at +1 and one pole is at -2. So we can observe that one pole now lies in the right half complex plane. Okay, so this is a very important difference. Now let us calculate the unit step response, and then like see what we get. Right. So let's do that exercise. Okay. So in this particular case, I will leave the partial fraction expansion to you as an exercise. I'm sure by now you know what to do. And if you have any questions, please let me know later. Okay. So what will be y of s? Y of s will be equal to p of s times u of s. Okay, and if we evaluate it, we are going to get this is going to be 1 divided by s squared plus s minus 2, right? Which is going to be equal to the following. So I will get y of s to be equal to 1 divided by s minus 1 times s plus 2, right? So that's how I will split that second order term in the denominator. And once again, we have three factors. So I will have three terms in the partial fraction expansion. So I'll have a by s plus b by s minus 1 plus c by s plus 2. Right? So these will be the three terms. And I leave this to you as an exercise. If you multiply both sides by s and substitute s equals 0, you get the value of a to be -1 by 2. Okay, so the residue a will be -1 by 2. Similarly, in order to get the residue b, what do? We multiply both sides by s minus 1 and substitute s equals +1. So we will get the residue as 1 by 3. I'm sure all of us can do this step. So once again, if you have any questions, please let me know. Okay. And to find the residue c, what do? We multiply both sides by s plus 2. And then like substitute s equals -2. So if we do that, we will get +1 by 6 as the residue for value of the residue c. Okay. So you can easily do these calculations. Okay. So I leave this to you as an exercise. Now, if I take the inverse Laplace transform, by now all of us are familiar with the process, right? So what will happen? The first term will become -1 by 2. The second term will become 1 by 3 e power t. And then the third term will become 1 by 6 e power, sorry, this will be 1 by s plus 2. Sorry, right? There is an error here. So this should have been 1 by 6 s plus 2. Okay, so please correct it. Okay, so the third term will be 1 by 6 e power minus 2t. All right. So we can observe that this is going to be the unit step response, the unit the response function or the output function corresponding to an unit step input. Okay, so this is what we will have. So even here we can make the two same observations, right? The poles, if you recall, the poles were at 1 and minus 2. So we can observe that the exponents are appearing as 1 and minus 2. Okay, so let me remove the 0. So essentially you can observe that 1 and minus 2 are the two exponents, right? So once again, the output function has the exponential terms, right? Output function is consisting only of exponential terms, and the exponential terms have the poles as the exponents. Okay, so that observation still stands. However, now what happens as t tends to infinity? What do you think will happen to y of t? What happens to y of t now?
Tends to minus 1 by 2.
It tends to infinity, right? Why? Because of e power t. Okay, yeah. So if it were e power minus 2, what you said is correct. Okay, it would have 10 to minus 1 by 2. But e power t is an exponential function with a positive exponent, right? And that will blow off to infinity, right? So
Yes,
is
sir.
it not?
Yeah, understood.
So,
Yes.
yes, yes. Okay, so I hope this is clear. So y of t will now tend to infinity. So if we apply the definition of bounded input, bounded output stability, I'm sure all of us agree that the unit step is a bounded input, right? Is it not? But the output is unbounded, right? Why? Because the magnitude is keeping on increasing, and the magnitude is going to infinity, it's blowing off to infinity as time tends to infinity, right? So this implies that this system is unstable. Okay, in the Bibo sense, right? In the sense of bounded input, bounded output stability. Whereas, although like it is not very evident currently, the previous example, right? The previous system corresponds to a stable system. Okay, so although like we essentially calculated only its step response, one can show that it's a stable system. See, to prove something is incorrect is always easy, right? We just need only one counter example. Okay, to show that the system is unstable. So if you look at the definition of Bibo stability, right? What was the definition of Bibo stability from the previous class? A system is said to be Bibo stable if its output remains bounded in magnitude for all bounded inputs and for all time, right? So please note the phrases that I underlined in red color, right? So the key phrases are all bounded inputs and all time. Now, like we have for system 2, we have readily shown that there exists one input, right? At least one input, right? Which is bounded, which is a step input, for which the output is unbounded. So once we show that, we can immediately conclude that the system 2 is unstable. Okay, system 1 is stable, although like we have only evaluated for only one bounded input, right? So now let me write down the general result. Okay, so is this reason fine? Clear? I hope this concept is clear. So from the example, I'm going to write a couple of generalizations. Okay, so what are these generalizations? An LTI causal dynamic system is Bibo stable if and only if all poles, okay, I'm writing in caps, all poles, okay, of its transfer function lie in the left of complex mode. Okay, so some people will say all poles should have negative real parts. Both mean the same thing. because we have already observed that if a complex variable lies in the left of complex plane, its real part is negative, right? So this is an alternative way of writing the same statement. Okay, so let me read this very, very carefully. A system is said to be bibostable, a linear time domain system is said to be bibostable if all poles of its transfer function, okay, lie in the left of plane. Okay, this is the criteria for bibostability. So now for system one, right? So let me repeat: a linear time invariant causal dynamic system is bibostable if and only if all poles of its transfer function lie in the left of complex, right? So for system one, we could see that both its poles, right, -1 and -2, were in the left of complex line, so it is bibostable. But on the other hand, for system two, one pole lay in the right of complex line, so it is unstable. Okay. So for reasons that we will see later, some people will say that, oh, okay, the system is asymptotically stable. Okay, so I'm just writing an alternative term which you will encounter. We will see what is asymptotic stability later on. But then the criteria is the same. Okay, so people may say a dynamic system is asymptotically stable if all its poles lie in the left of complex. Okay, so that's a different statement which you will encounter. Now, the second result is a LTI causal dynamic system is unstable even if one pole of its transfer function lies in the right half plane. That is, has a positive real component, a positive real component. Okay, so this is the counter result. Okay, so essentially, when we call the system as unstable. Okay, so and there's something which we saw in the previous example, right? In for system two, essentially one of the poles, right, was at +1, and so the system output blew off to infinity, right? So when time tends to infinity, right? So even for a bounded input like a step input. Now, the question is, what happens when a pole or poles, multiple poles, sorry, 1 minute, let me rewrite this. Okay, when a pole or poles lie on the j omega axis or the imaginary axis. Okay, so we know that the S plane, as we know, as we have drawn here, the S plane has this real axis and the imaginary axis, right? The imaginary axis is what is called as the j omega axis, right? This is something which I already pointed out. So now the question becomes, what happens if some poles lie on the j omega axis? Okay, so the reason why it's called j omega axis is very simple, right? So suppose in general we consider any complex variable, right? So that is of the form sigma plus j omega, right? On the imaginary axis, the real component is 0, right? Is it not? So on the imaginary axis, sigma is 0. Okay, so this would imply that S would take the form of j omega on the imaginary axis, right? So that is why people call it as the j omega axis, right? So that is the reason behind it. Okay, so now I am going to leave you with this exercise problem to solve. Okay, like as part of this today's class. Okay, and then we will discuss its solution and the consequence in the next class. You don't need to submit it as a homework. Okay, so you can just do it as an exercise and come to the next class. So I'm just giving this problem. So consider the second order system whose governing equation is given by the following. Whose governing equation is y double dot p plus y dot p is equal to u of t. Okay, so this is the governing equation of this second order system. Okay, so now what I want you to do is the following. So determine its transfer function, derive its transfer function first. So similar to the process that we have already done in today's class, and calculate y of t for two inputs. Okay, u of t is 1, the unit step input, and the second one, u of t is equal to sine t. Okay, I'm giving you two bounded inputs. Okay, the unit step input and a sinusoidal input, right, with unit angular frequency sine. Okay, so please calculate the system output for these two bounded inputs. And as I mentioned, you don't need to submit it as a homework. Like this is an exercise, but please do the problem and come to the next class. And then we will discuss the observations and the consequences. Okay, as to what happens when we have poles on the imaginary axis. Fine. All right. So any questions based on the content that we have learned today? Okay, so if there are no questions, let me stop recording.